So for this lesson we begin our next unit, which covers exponential and logarithmic functions. Exponential functions should be a review, but logarithmic functions are probably something that you haven't seen before. And if you have seen it, you may have seen it in your chemistry class, for example, or something along those lines. Now, the logarithmic function comes up actually in a lot of natural sciences, and it's really wherever we use exponential functions to describe something, the logarithmic function is how we solve many of those problems. And so it is the inverse of an exponential function. So we're going to talk a little bit more about that in a moment. But let's just quickly talk about exponential functions to start. Just a quick review. So if I've got f of x is equal to 10 to the x, when we talk about exponential functions, we are talking about something that has a base and then the exponent is our variable. So 10 to the x is obviously not the only exponential function. We could have 2 to the x, we could have 100 to the x. This base value can be any number of values. There are some restrictions on that base value that we're going to be talking about shortly within this lesson. But 10 to the x is an exponential function. That's a valid base. So f of 3 in this case is just a replacement. So that's the same as 10 to the power 3. And then we evaluate 10 to the power 3, which is equal to 1,000. That's not particularly interesting, other than the fact that it lays down the groundwork. Well, what is an exponential function and how do we interact with it as a function? But now what if we get asked to solve an exponential function? That gets a little bit more interesting. So now if we're asked to solve f of x equals 100, that's the same thing as saying that 10 to the x is equal to 100. And although I'm sure many of you can just look at this and tell me what the solution is, the more formal approach to doing this is to write the left side and the right side using the same base. So 10 to the x is equal to 10 to the what? So 100 conveniently is just 10 squared, or 10 to the power 2. And if 10 to the x equals 10 to the 2, the base is being the same, then that means we can, from here, we can understand that x must be equal to 2. And that's how we end up with our solution there. But things are not always quite that straightforward. So let's go to our third example here. F of x equals 37. 10 to the x equals 37. And obviously that is not going to work out because 37 cannot be represented as a power of 10. We do know a couple of things. We know that, for example, well, 10 to the 1 is equal to 10. 10 to the 2 is equal to 100. And so where does 37 lie in that range? Well, it's going to be somewhere between 10 and 100, which means my exponent has to be somewhere between 1 and 2. And so for this, I might try different values. I might try 10 to the 1.5. And I might try 10 to the, and it works out, turns out that it's approximately 10 to the 1.6. That's what gets me closest to my value on this one. So 10 to the 1.5 gives me 31.6, approximately 31.6. 10 to the 1.6, on the other hand, gives me 39.8. So that's a better result, but still we could do better still. So I might try, well, halfway between those, 10 to the 1.65 and 10 to the 1.65. That's equal to, oh, I'm sorry, I didn't mean to do that. Not 1.65, I should have gone 10 to the 1.55. And that's approximately equal to 10 to the 1.55, 35.5. And so on and so on and so on. And I can keep refining this answer until I get as close to 37 as I want to be. So if I specified that I wanted something that was 37.000, and then the rest of this might be some other digits, I could continue to refine my answer until I got to this specified level of precision. Might take me a long time. But this guess and check method, while it's valid, is really not something that we as humans want to have to do all the time. It's quite time consuming, especially when you're trying to get to this high level of precision. So how do we get around that? We can make use of if we had it available to us, we could make use of the inverse of an exponential function in order to go directly to this. And that's where we're going, the direction we're going with this new unit, which is logarithmic functions. Now, a little bit of history, but I'm not going to spend much time on this. So the person who gets credit for logarithmic functions, John Napier, this occurred in the 17th century. And just as I said, guess and check, while it's a valid method, is not a particularly efficient method. And John Napier essentially was thinking through the fact that there were a number of problems that were coming up that had no effective numerical tools to deal with them. And in particular, it was exponential functions. And so he came up with this logarithmic function. And there are a number of areas. I'm not saying that he necessarily was concerned with these particular areas, but there are a number of areas in the natural sciences where logarithmic functions are essential for doing the work. So pH levels in chemistry, exponential growth and decay problems in biology, sound intensity, light intensity from physics, and the Richter scale, which is how we measure earthquakes in physics and geology. All of those make use of logarithmic functions. Okay, so logarithmic functions are the inverses of exponential functions. So the way that we find an inverse traditionally is we swap the positions of the x and y variables. So essentially we are swapping the independent and dependent variables. And the other thing for you to keep in mind is that a function and its inverse undo each other. And I'm going to explore that a little bit more on the next page to illustrate what I mean there. If I start with this exponential relation, y equals a to the x, I mentioned this on the first slide, the base of your exponential function actually has some restrictions. And for those of you who may recall what you looked at in your grade 11 course, you actually went through this. If you put in a negative value for a, there are going to be values of x that give you, for example, you'll be trying to take a square root of a negative number, that sort of thing. So negative values get excluded, and 1 gets excluded because 1 to the x is always 1. Well, that's not an exponential function. So we start with this as our standard parent function for the exponential. We swap the x and the y. So we end up with y equals a to the x becomes x equals a to the y. But unfortunately, we have no algebraic method for rearranging this. There's no operation that we know of as yet that can let me, first of all, take this y out of the exponent and bring it back down, because from here, my goal is to rearrange it into something y equals. So what Napier essentially did was to say, I'm going to have to redefine something. So this form, x equals a to the y, I'm going to redefine a new function, logarithm, that is the rearrangement of this equation. So since we don't have a way to perform the rearrangement, he just said, well, I'm going to assume that there's an answer at the other end, and I'm going to call that a logarithm. So x equals a to the y becomes y equals log base a. We still need to be aware of the bases of x. Same restrictions on a. So it has to be a number that's greater than 0, but it's not equal to 1. And these are what essentially it's saying is that this logarithmic form is equivalent to when we swapped the x and the y of the exponential. Now, before we explore that any further, I just want to remind you this idea of functions and their inverse undo each other. You're already familiar with that concept and you've used it quite a bit. And so all we're doing is we're just adding another function and its inverse to that group. A function is like a machine in the sense that it accepts an input and it produces an output. So if I have a function that is x squared, if I give it the input of 3, its output will be 9. But x squared has an inverse concept. How do we reverse or undo a squaring? We take a square root. But notice that if I have an input of 3, which gives an output of 9, and then I take that output and I use it as the input to the inverse, an input of 9 through a square root gives me an output of 3. So if you look at this as a big picture, if I start with 3 and I take the number 3 and I run it through the function, and then I run the result through the inverse, I end up right back where I started. And that is this idea that they undo each other. If I take pi by 6 and I put it into the trigonometric function sine, I get a result of 1/2. But if I then take that result and put it into the inverse function of sine, which is sine to the -1 or sine inverse, I end up back at pi by 6. Now I realize I'm oversimplifying things. You might say, well, hold on, the sine inverse also has an answer of 5 pi by 6. And that's true. But if I put 5 pi by 6 into sine, I also get 1/2. So yes, it can be more complicated. It can be complicated by the idea of I could also put in 5 pi by 6 and I could also get the answer of 5 pi by 6. I don't want to oversimplify this too much, but I don't want you to lose sight of this idea that the function and its inverse undo each other. So now let's take a look at something like this. I have an exponential function, 10 to the x. 2 goes in, turns into 100. 100 goes into the inverse, which is a logarithmic function. 10 to the x, the inverse of that is log base 10 of x. I take 100, I put that in, I get 2. So they undo each other. Whatever it is that an exponential function does, its corresponding logarithmic inverse undoes it. And so in general, if I take the value x and put it into 10 to the x, I get some value y. If I take that y value and put it into a logarithmic function, I get x again. Whatever that x is, I get it again on the other end. And this is actually a very useful property, and we're going to be developing this and we're going to be learning how useful it can be. Okay, now as far as logarithmic functions, because a logarithmic function is in the form y equals log to the base b of x, where b is greater than 0, b is not equal to 1. Now notice I just changed. We were talking about it as being a before, now I'm saying b. I want you to understand it doesn't matter what letter we use here. Both are valid. We are going to be switching over to b simply because, and stands for base, so it makes sense, because when we start doing transformations, a, k, p, and q, we already use a value for a. So I want you to get comfortable with the idea that you may see it in notes and in textbooks, etc., as log base a, which is typical, but from a practical point of view, when we refer to it, we're often also going to switch over to log base b. Now, the two most common bases for a logarithm are 10 and e. Now 10, that makes sense to a certain extent because we think in terms of base 10 all the time. Our number systems are base 10. We count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. And then we go to 100, etc. Scientific notation, we write numbers like 3.2 times 10 to the 5. Powers of 10 are very convenient. And so that's the reason why log base 10 is a common, well, known as the common log. If you ever see a logarithm without a base, it is understood that the base will be 10. There's another quantity known as e, and e is the natural number. It is a number like pi. First of all, it is an irrational number. It is a non-repeating decimal. But it is also a number like pi in the sense that through experiments, through scientific experiments, it is a number that just showed up. And in the case of e, it showed up time and time again. In the case of pi, it came out of a very specific direction, which was to look at the relationship between the circumference of a circle to the diameter of a circle. Whereas e came out of other types of experiments, and it just kept popping up again and again. So in natural science, that's why it's called the natural log, log base e gets its own special name, which is ln, the ln of x. We're not going to do much with this unless it comes up, but we can solve it. It's just another logarithm. But for those of you who carry on with math and looking into calculus and then going further than that, and those of you who go on to do work in other branches of science, particularly physics, this is going to come up quite a bit. Okay, so now we've been asked to write an equivalent exponential expression. Now to do this, what I want you to keep in mind is the relationship. And there's two ways you can remember this. So you can remember y equals base to the x has an inverse relation, which is going to be x equals log to the base b of y, which is equivalent to x equals base to the y has an equivalent relationship y equals log to the base b of x. You'll notice here this was my original exponential function, and here's what that function means as a logarithm. Or I took my original exponential function and I swapped x and y, and then here's the corresponding logarithmic function. All that really matters is that you see the positions of the y and the x, and you recognize how those values change as you move between the inverses. So let's go ahead, and it doesn't matter. I'll refer to both of them. I'll show you it doesn't matter. Here I've got log base 2 of 32 equals 5. And this is true. So I'm not trying to prove whether this is true or false. This is true. I want to write another expression that says the same thing. So since this is a logarithmic expression, I want to write this as an exponential expression. So in an exponential expression, here's my base. So log to the base b, well, that's going to become b to the something. So here's my base, that's 2. 2 to the power what? Okay, well, what corresponds to my exponent here? Here's the exponent. In a logarithmic expression, the exponent is the number that's all by itself on the other side of the equal sign. So that's this 5. So that goes there. And then that's equal to 32. And we step back for a moment. 2 to the power 5 is equal to 32. Yes, that's correct. For this one, well, this is log to the base 10 of 1 equals 0 because there's no base mentioned here. So normally I wouldn't rewrite this, but to start, I just want to make sure everyone sees that. And so now I know, well, that my base is 10, so this is going to be 10 to the power. 10 to the power what? Where do we get our power from? It is log to the base b here. The power here is x, which is the number by itself, so this is the 0, equals, and then what was inside the logarithmic function, log base b of y, that means my y value is this number 1, but that comes outside on the exponential. And so is 10 to the 0 equal to 1? Yes, it is. And just to show you, so I used the red one there. I just want to show you the green one is just the same. I'll use that for these ones. 3 to the power 4 equals 81. 3 to the power 4. B to the power y. So 3 is my b. So that means it's going to be log base 3. My y value was 4, but that means 4 is going over here on the outside, equals 4. And my x value is the 81, that goes into the logarithm. So that is log to the base 3 of 81 is equal to 4. And putting this into English, it's basically saying how many times do I multiply 3 by itself to get an answer of 81? And the answer to that is 4 times. Whereas this one is saying take 3 and multiply it by itself 4 times, and you will get an answer of 81. 1 over 16 equals 4 to the negative 2. So on this time on the right side, I've got 4 to the negative 2. 4 to the negative 2. So this is log base 4 to the negative 2. So my y value is negative 2, so that's going to go over here. Log to the base 4 of 1 over 16. And you can always, for any of these, if you prefer, you can always write that as with a bracket. Just in the same way that we can write sine of pi by 6, but that's also sine of bracket pi by 6. And that's just to remind you that it is the sine of this. This is my input. So either of those is perfectly fine as far as representation. As the argument of the function gets more complicated, you will have to use this bracket in some cases. Okay, so that's it. There's our introduction to the logarithmic function, which is the inverse of the exponential function.